let's take a look at this question here. Okay, which must be true on this interval. So notice we're given information about the derivative and asked for information about the original function. So the original function has to be concave up on this entire interval. The original function has at least 2 points of inflection. The original function is increasing. The original function has no critical points. Or the original function has at least 2 relative extrema.
C.
I think the original function has to be increasing for the whole interval?
Yeah.
Why?
Because everything on there is positive. It is above the x-axis.
That is true. But we don't know what the y value at 1 is, right? Y value at 1 could be down here.
I hate you.
We don't know that for sure. What do we know for sure, though? What would have to happen based on this information?
Well, it's not A.
So what would have to be true for the graph to have relative extreme? Yeah, mins or maxes. So those would occur where the first derivative equals 0, right? Well, we're also not guaranteed that this derivative equals 0 because from our original picture of what could be happening, it never crossed the x-axis, right? So that one doesn't have to be true either.
So it's either B or B. Not A.
B, right? Because you can see the slope goes from increasing to decreasing.
Right. Somewhere on here, okay, we're not sure exactly where. I mean, from what we've drawn, it looks like it would happen in 0 and 5. Okay, but somewhere on here, the second derivative will equal 0 twice. Right? The slope is going to change from positive to negative or negative to positive for my first derivative at least twice. It could happen here, it could happen here, it could happen over here somewhere, but from this information, we know for sure it's going to happen twice. So this graph, the original graph, will have at least 2 points of inflection. You okay with that one? Alright, so let's talk about 2 days worth of homework now. So let's start with the approximation AP questions. Right, I sent you guys all the worked out solutions, but we can still talk about any questions that we have. Let's see, do I still have this open? Probably not. Okay.
So much reason calculator to just be.
Let me open it up here.
No, I did it. What did you do? You're I have a question on 4.
4? Alright, let me the
Oh, I guess me too because I haven't started.
where's this? Where on earth did I put this? Should I put it here?
I think you have too much on your computer.
There it is. I found it.
That'll be making that up real fast.
Alright, this number 4, the multiple choice number 4. It's still frozen.
Yeah, I had to look how you wanted to.
Did you put the answer?
I did, yeah. And I sent them to you in the reminder too. So
the same reminder you told us that this is where I put the hand.
no. Yeah, I sent out the answers Monday night. So for this one, okay, it says the flow of oil in barrels per hour through a pipeline is given by the graph above. Okay, so we haven't really talked about this a whole lot, but barrels per hour, that means that's a rate. Okay, that's kind of like our velocity function. It's a rate, barrels per hour. We want to figure out then how many total barrels have passed through the pipeline. What that means is find the area under the curve. Okay, if I'm given a rate and I want the total number of something, that's like given a velocity and asked for position. So I want to find the area under the curve, or an approximation for the area under the curve. Okay, well, the best approximation is probably going to be to split this up into a couple of different pieces. Right? Now, we don't have any way of finding the exact area, but I can come up with a pretty good approximation here using a couple of rectangles and a couple of trapezoids. Right? So here, this first one is 6 by 100. So this area would be 600. Then this one's going to be the same, right? 6 by 100. Okay, now I want to find the areas of these trapezoids. Now, remember, if you ever forget how to find the area of a trapezoid, okay, especially if you forget on the AP test, you can just split this up into a rectangle and a triangle, okay, and then find the area of both of those pieces. Okay, so if you forget the area of a trapezoid, don't panic. Okay, just split it up into pieces that you do know how to find the area of. So, I mean, in this case, that might actually be easier because I already know that these blocks are going to be 600, right? So if we're trying to do this quickly, these are all going to be 600. Then here, these are triangles that are exactly half of one of those rectangles, so each of those would be 300. So if I add all that together, 600 plus 600 plus 600 plus 600 plus 300 plus 300, we get 3,000. Okay, so on this one, it did not tell you how to approximate the area under the curve, right? And all the other problems, it said, use a left approximation or a trapezoidal approximation or whatever. Here, it did not. It just said, figure it out. Okay, so it was up to you to determine the best way to approximate the area under the curve on this one. All right. We okay with that one? All right, what else?
I know you said we have money yet, but where does like the 171 with the 180?
Yeah. So, we'll probably go in depth into that. I mean, like, there's a whole lesson on what that actually means. Probably not for a couple of weeks, actually. But the short version of what this means, and it even kind of tells you right here, this is a way of finding average value. Okay, so if we're given a function that gives me the rate at which temperature is changing, okay, and I integrate that, that'll get me the average temperature. Okay, if I have a function that gives me the temperature, I integrate that and then multiply it by 1 over b minus a. Okay, so here my x interval, okay, I went from 0 to 20. If I multiply that by 1/20th, that'll get me the average change for each piece, which ends up being the average value for the whole thing. Same idea on, which one was the other one?
So we didn't have to do the ones.
Did I cut that off up here? Yeah, there we go. So just the part where it says explain the meaning, we haven't really talked about what this actually means yet. So like I wrote that out in the explanations, right? So I mean we should be able to do this first part. I use the trapezoidal sum to approximate the area under the curve, but we haven't talked about, like, in terms of a problem like this, what this actually means, like for a real world application yet. So just like the last one, okay, whenever I have 1 over the difference between my starting point and ending point, that's talking about average value.
So the 1/8 in front would be the thing you're trying to find the 7. Like when you're trying to find the area.
Correct. Yeah. So we would want to do this first, right? Just find the area under the curve first, and then multiply it by 1/8, right? In terms of this problem. So I have a whole lesson on what this actually means. Okay? It just ends up being finding the average value of something. Okay, but for right now, we're just focusing on finding the area under the curve using approximations. Other questions on these approximation questions? Okay, then how did the lesson go yesterday? Pretty good? Alright, so I woke up early in the morning and did that, so I was still a little groggy. So I made a couple of mistakes on there, but I think I caught all the mistakes as I was making them.
I kind of wanted to like yell at you because I'm like, you're doing that wrong. You're doing that wrong. Ugh.
But then I caught
Yeah.
Yeah, the one where you like were all kind of wrong. I like sat there for a second and I was like, wait, dividing that is multiplied by half again.
You were also
Yeah.
improving. I remember, like, you convinced me though. I thought that you were right. I wrote it down on my list.
I didn't. I was like, what the
I knew it was wrong, but I was like, wait, maybe I'm the one. Maybe I don't know.
No, it was definitely me. So no questions on any of that stuff on the Math Excel or anything? Felt pretty good.
It looks exactly like
Oh, I know what you're talking about. Sums.
yeah.
Oh,
That's what it reminds me.
summation notation, yeah.
I kind of
I remember freaking out when I saw them.
All right. Well, if there are no questions on that, I actually.
That'd be expensive.
So she's not. She's my second cousin, I guess.
I like the ones that leave the first number. I don't like the ones with
Wait,
variables?
the ones where you're just finding the area of a rectangle.
Supposed to be 49 on that. It was less than 33 or 43. We can go down. Like Matt and I were gonna find shells and paint them.
As long as things like to do, they can.
Oh my god, let's cut some.
All right.
No. Cold that? No. We can't do that.
I'm ready.
Me too.
Next one.
It's like a something minus.
It's A squared.
All right.
A squared minus B squared.
I don't know.
Equals C squared.
I don't know why.
So yeah, let's try to figure some of these out. Okay, so today we're going to talk about properties of definite integers. So the first one says I'm starting and ending at the same x value. What would the area under the curve be if I'm starting and ending at the same x value?
QA.
Wait, I think zero, right? If I'm starting and ending at the same x value, there's no width to my area, right? So therefore there can't be any area.
Unless it's a
Or
circle.
A minus A is the same thing.
Wait, how? What do you mean? What if it's a circle?
Like, because it goes, woo!
So, so we're thinking about area here, right? So if I've got a circle, the area inside of a circle is still a positive area.
Yeah. So it wouldn't be zero.
Right, but that wouldn't be the situation.
Yeah, when it starts, it stops at the same place.
Not, not at the same x value, because if we're taking the area of a circle, we'd be starting at this x value and ending at this x value.
No, it starts at the bottom, goes back, then comes around. So there.
So what this is saying, right, is if we have some curve, and I start at A and end at A, there's no way for me to accumulate any area. Right? If I'm starting and ending at the same spot, the area under the curve would just be 0. Right? Our next
I understood
property,
what you were going at.
okay, says that if I take some value in between A and B, right? So if we've got this same picture, and I'm going from A to B, and I'm taking this area under the curve. Okay, so this would be a positive area. This isn't the same thing as number 1. Then what I can do is split this up into 2 integrals. If I take some value in between, call it C, right, I can just make this 2 different pieces. I can say this would be the same as the area from A to C of my function, plus the area from C to B. of my function. This is pretty ridiculous.
So, okay, why don't we just take the whole thing at once?
Well, we looked at, in the video from yesterday, we looked at an example where it made sense to split it up into pieces, right, where we had positive and negative area. That would be one situation. We're going to look at other situations where we have multiple curves intersecting, where we'll need to split it up into multiple pieces. So I mean, the majority of the time, we would just want to take it over the whole interval, but there are special cases where we'll want to split it up. The next one says that if I have my integral from a to b, and I say that that equals some value, we call it k. If I flip my bounds, okay, if now instead of going from a to b, I go from b to a,
Negative k.
exactly. Okay, I'm going backwards. We say this is just equal to the opposite of the area. Okay, negative k.
So if but if the like A or B is negative, then your value is that the value is still positive, or is that the value? You know what I mean?
So
Like the area, not the value, the area.
if one of your bounds is negative, that's just talking about the x value.
Yeah, so it's still positive.
So yeah, I mean, if our area was positive, this being a negative x value wouldn't change that, right? That would just be like starting over here, right? So all of this area is still positive. It depends totally on the y values, whether the function is above or below the x-axis. All right, so on this next one, okay, given that b is less than a, okay, this one is actually really similar to this one, okay? If we're saying that this value is less than this value, right? So for example, I'll write an example over here. If we're going from 4 to 1, okay? We're saying that this value is less than this value. This is really similar to number 3. We can just say this is equal to the opposite of b to a. Okay, we can just throw a negative sign out in front of the integral. Our fifth property, if we have some constant being multiplied by our function, okay, for example, if this were like the integral from a to b of 3x squared dx, right, if we just have some number out there, what I can do is pull that number out in front of the integral. Okay, and then not worry about that number when I'm going through the integration process, and then just multiply by that number later. So this, in our example, I can pull that 3 out front. Just make this x squared dx. Okay, that property is actually pretty useful for making calculations less complicated, okay, especially when we talk about the way to find area under something like this exactly. All right. Our sixth property here, if I'm adding two functions together inside of an integral, for example, just like x squared plus x, right? I can split that up into two separate integrals. I can say this is the same as the integral from a to b of f of x dx plus or minus, whichever one we're talking about, the integral from a to b of g of x dx. Right? For example, if we've got the integral from a to b of x squared plus x, I can split that up into two separate integrals. Say x squared dx plus the integral from a to b of x dx. Okay, so that works with addition or subtraction. All right, any questions so far? Alright, so then the last couple on here are even and odd functions. What is an even function?
2.
That's an even number. What's an even function? What does that mean? Exactly. It's symmetrical across the y-axis. What that means is the area under the curve will also be symmetric across the y-axis. So in this example, it says I'm starting at negative a and ending at a. Well, I can then just take twice the area from 0 to a. Right? If I take this area right here from 0 to a, that's going to be exactly the same as the area from negative a to 0. Okay? Sometimes this comes in handy, especially if we're just given information. And we'll look at an example of this. Like if we're just told the area under the curve from 0 to a is 7, what's the area from negative a to positive a if this is an even function? Okay, something like that. So this property definitely comes in handy. What is an odd function then? Symmetrical about the origin. Exactly. So what that means, if I'm taking the area from negative a to positive a, these areas here will be the same. So since this piece is below the x-axis, this piece is above the x-axis, if I add them together, 0. Okay, if we are told that we have an odd function, then the area from negative a to positive a, as long as those two are exact opposites of each other, the net area will be 0. All right. Questions? All right, let's take a look at some examples. All right, so we are just given two pieces of information here on the back. We're told that for some function f, the area under the curve from 0 to 3 is equal to 6, and then the area from 3 to 7 is negative 8. Okay, that's all I know. From that, I want to answer all of these questions. Okay, so let's do a few of these together. So the first one is just, well, if the area from 0 to 3 is 6, what's the area from 3 to 0?
Negative 6.
Negative 6. Okay. We're using the property where if we flip the bounds, we just take the opposite of the area. Well, how about the area of this function from 0 to 7?
Negative 2.
I would add these two pieces together, right? From 0 to 3 and then 3 to 7. Add 6 and negative 8. Get negative 2. How about the area from 3 to 3?
0.
0. Right? If I'm starting and ending at the same spot, there's no way for me to accumulate the area. How about the area from 7 to 3 of 3 times my function?
Negative 3.
Okay. So, wait a minute. I think I heard all of the pieces.
That just need to be flipped. So it's 8 times 30.
Right. So I can just pull this 3 out front, okay, and say, well, this will be 3 times the area from 7 to 3 of my function. Well, I know the area from 3 to 7 is negative 8, so the area from 7 to 3 would be positive 8. So 3 times 8 is 24. All right. Why don't you guys try the rest of them here?
Really?
There's only 3.
Give us the whole ones.
Okay. This 5th one you'll have to think about a little bit.
Yeah. I'm thinking about it.
So we're adding 2 things together here.
Maybe it's just for the first one, and just 2.
Yeah, so we can say that our first function is 2 if I'm splitting this up into 2 different integrals.
I'm gonna pull out the 2 in front of that one.
You could.
It would be positive 16 minus 24.
How'd you get 16 for this one?
100 get
So my function is y equals 2, and I'm going from 3 to 7, so I'm finding the area of this rectangle. Height of 2 and a width of 4.
Okay.
So this one, we've got the function. This was 6. 6 is 12. Did we get negative 16, 12, and 0?
So for the even one, if it would have said like 0 to 0, that would work. Like if it would have said like 2 and negative 2 would have still 12. Or like if they were okay, if they would have the same function or whatever, or like the 7 negative 7, would that have been negative 16?
So if they would have done 7 to negative, or negative 7 to 7,
Yeah.
we already found in a previous problem the area from 0 to 7 was negative 2, right? So then we would just say, well, this is equal to 2 times, 2 times the area from 0 to 7, which would be negative 4. So when we split this up into 2 functions, right, my first function is just 2. So this is what we did in the lesson yesterday, right? Finding the area under a curve like this, which is just a horizontal line, y equals 2, from 3 to 7. So I'm just finding the area of a rectangle with a height of 2 and a width of 4. Okay, so we're already starting to combine things together here from previous lessons. Okay, any other questions on these? All right, then the last page, okay, is getting some of this information from graph. Okay, we haven't actually looked at problems where we were already given a graph. Okay, everything we've looked at so far with this notation has been we had to create our own graph. So let's, given this graph right here, try to figure out some of these things. So first, okay, this one says find the area under the curve from x equals 0 to x equals 3. Right, so I want to find the area from here to here. So I'm finding all of this. How can I do that?
Well, there's a triangle over here. 2
Okay.
from 3.
Yeah, so let's try to split this up. Alright, so I mean first, this is a semicircle up here. Right? This whole thing is a semicircle, which means this piece that I care about from here to here is a quarter circle. And then down here, this would just be a trapezoid, or we could split it up into a rectangle and a triangle, which however you feel comfortable. And so we could split it up like that, or we could just take the area of this whole thing as a trapezoid. So how do I find the area of each of these pieces?
Oh,
Yeah. So our circle would be pi r squared over 4, okay, if I want just a quarter of a circle. So my radius is 2. So pi times 2 squared over 4 gets me that this piece, this area is just pi. Okay, and then again, whichever way you feel comfortable, you can find the area of the rectangle and the triangle separately, or the area of the whole trapezoid. I'll split it up since that was suggested. So the area of this rectangle would just be 2 times 1 is 2. The area of the triangle would be 1/2 times 1 times 1. So 1/2. So what's my total area? What's the answer to this problem?
2.5
Plus pi, right? So I like improper fractions. I'll write it as 5 halves. Okay. What about the value of the integral from 0 to 4? Alright, so we already found all of this from 0 to 3. We just need to add on this piece now. Okay. So what's the area of 1/2? Right.
So
So
it'd be 2 plus
exactly. Since this is below the x-axis, we say this is a negative area. So this answer, the area from 0 to 4, would just be 5 plus 2. Alright, so you guys try the rest of these here.
Antiderivative.
Oh wait, maybe I didn't read the last couple. What is that? Does it say something about the antiderivative?
Yeah.
Oh yeah, don't worry about those.
Okay, so just do.
Yeah, just that one then. We haven't talked about antiderivatives yet.
That scares me.
It's not that bad. It's just if I tell you this is the derivative, what's the original function?
2 squared.
X squared.
Yeah.
X squared. That's all antiderivatives are. We're just going backwards.
What if there's something like we can't be sure that
You're actually right. There's some we can't be sure of the exact function, which we'll get to that.
You're like, not today.
Not today. All right. So what's our answer to this last one here?
5 plus 2.
5 plus 2 pi. So really, all we had to do was take our answer from 0 to 3 and multiply it by 2, right? Because I can see that this is an even function. So we didn't have to go through all the work of finding this area as well, because it's the exact same. So we just did 2 pi plus 5, or 5 plus 2 pi. Questions on properties of integrals?
Flippity flop.
Flippity flop.